Hi, this is Abigail, and today I'm going to be talking about Physics Lab 1 on constant velocity. In this lab, we'll watch an object, in this case, an expo marker, moving with a constant velocity across a table. Newton's second law of motion will be used to explain what is occurring. We will examine the reality model from a tracker in addition to a computational model with the predicted outcome. This lab's goal is to examine an object moving at a constant velocity, determine how well the tracker and computational models match up, and discuss reasons that may cause them to differ. So the main physics ideas presented throughout Lab 1, the main one is Newton's second law of motion, also known as the momentum principle, where the net force is equal to the change in momentum over the change in time. In this case, we don't have a change in momentum because the velocity remains constant, so the net force is just going to be zero. And the velocity formula. So I included this because I wanted to show that the final velocity is going to equal the initial velocity because our net force is zero in this case. Because the zero in F delta T is going to be zero divided by the mass, it won't really matter. So. Alright, for this experiment, we recorded the motion of a marker with a meter stick in the background. Then I imported the video into Tracker and calibrated the axis according to the marker, and I also tracked the marker along time frames at certain points. And then using the star code as a base, I coded and calculated what would happen if everything was predicted ahead of time. And with this, I also used the initial conditions from the tracker and was able to determine the velocity from the first couple points of the tracker data as well. And so with all this data, I created a position versus time graph using both sets, and we're going to compare them today. So I wanted to include the end of my code to show that applying the momentum principle and using the updated velocity and updated position formulas, that's how I did the end of my code, and then delta t was 0.0333 seconds. And up further, you would see the initial conditions as well, but I just wanted to show the end of my code there to show that the velocity really wasn't changing. So this is my data. You can see the tracker data is in blue and the GlowScript data is in red. You can see at the beginning of the graph, the points are very close together and then they spread out. So let's talk about some discrepancies, like how these discrepancies could happen. You can see there are slight discrepancies, and that could just be due to the table not being fully level, human error, pushing the marker, touching the marker, or whatever, not touching the marker, but pushing the marker. And then the tracker also, using tracker for the first time, you could also have some discrepancies as well. So, and then also at the very beginning, we could be seeing some slight acceleration because of where the data started. So that could be the reason why the data doesn't fully line up. But they are pretty close in the beginning, and even towards the end, they're still pretty close. So, all right. So, what if and what does it mean? Well, how would my results change if I change the axes in tracker? So, it's going to change your data, of course, and the way your graph looks. Like if you move the axes to the middle of your marker's trajectory, it's going to split your data in half, negative for the first half, positive for the second half. And you're going to see that data move towards the origin, then move away, like we saw it moving away. And so it's just going to shift your data. And that's also going to happen if you just made the data negative. It's just going to make your data negative. So yeah. And then, is it possible for me to say how many pulls and pushes or how many forces are added together to give zero net force in the case that you observe? So in our case, we assume there's zero air resistance and zero friction. So for this, we can just use Newton's third law of reciprocity to determine these forces. Every action has an equal opposite reaction, pretty much. So the force of the table on the marker is the same as the force of the marker on the table. Same with the force of gravity. Same with the marker, just rolling across the table. Because we assume there's no friction, we assume that those forces equal out as well, which means there's zero net force observed. And then also, as we saw earlier, net force change momentum over time. So because there's no change in momentum, and there is change in time, doesn't really matter because zero divided by anything is just zero. So thanks for listening to my presentation. I really appreciate it. Have a great day.